Okay, so let's remember where we were. We had analyzed this circuit here. We'd walked our way around it. We'd gotten an equation. Here's my differential equation. We solved the differential equation by noticing it was the same differential equation as we had before, just I instead of Q. And here's the solution. We looked at it before. What's this tau? Well, this tau was L over R. And what does this solution describe? Well, it describes a current that's 0 initially, because when you first close this switch, the inductor fights the battery to a draw. No current flows initially. But as the current starts flowing, that reduces the voltage drop across the inductor, increases the voltage drop across the resistor in a way which is described by this solution. So initially, no current. At the end of the day, late times, the current is now flowing in such a way that it's as if the inductor isn't even there anymore. The entire voltage drop is across the resistor. All of this we described last time. What I want to do now is I want to ask, does it make sense that this L over R quantity is a time? You know, we got it out of the math. We got it out of the math. Out of the math, we found that there's this time tau at which the current has risen to 1 over E, Euler's E, 1 over little e of its final value. And that's this time tau. And it just came out of the math. And there's this E here and just felt like a mathy thing. So when you're a physicist and you get to something like this, what do? Well, the first thing you do is you check dimensions. You say, well, wait a minute, does it make sense that this L over R is a time? So what are I ask myself, what are the dimensions of L over R? And the dimensions of L over R are going to be the dimensions of L divided by the dimensions of R. And now, how do I figure out what the dimensions of L are, what the dimensions of R are, without going to look them up? Well, I have to think of an equation in which R occurs where I know the dimensions of everything else. And for me, that's Ohm's law. So I remember my Ohm's law. Ohm's law was V is equal to IR. That means that the units of R are the units of voltage divided by the units of current. So the units of R are volts over amps, over amperes, or amps. Okay, so the units of R are the units of voltage divided by the units of current. Now I need an equation in which L occurs. Well, that's an equation that we've had relatively recently. We have had an equation written on the board not so long ago in which epsilon was minus L di by dt. And this equation, this tells me that the units of L are the units of electromotive force, that's volts, divided by the units of di dt. So the units of L are volts, divide by di dt, and that's amps over time, or seconds. So what I conclude then is that the units of L over R, well, the volts cancel the volts, the amps downstairs cancel the amps downstairs, and here I have a 1 over time, which is downstairs, and so the units of L over R are, in fact, the units of time, which is to say seconds. So this is nice. This is a physicist's way of checking that I didn't make a mistake in doing the math. I do the dimensional analysis, and I see that this quantity here really is a time. And it's the time that you can get by combining an L and an R. So doing this makes me think, well, maybe I should have done that for the RC circuit. I didn't actually do this exercise, but let's do it now. So let me first erase this just because I need the space. And if I cast my mind back to our discussion of the RC circuit, there was a time constant there also. And the time constant there was RC. So let's just check that in the same way. Let's ask, what are the units of RC? Well, the units of R, we did that already, volts over amperes. Now, what about the units of capacitance? Well, remember that with a capacitor, the voltage across the capacitor was given by Q over C. That's an equation that I remember. That tells me that the units of C are the units of charge divided by the units of voltage. So the units of charge, that's coulombs, divide by volts. The volts cancel, and now I have coulombs over amperes. But then I remember that an ampere is a coulomb per second. So this is coulombs divided by coulombs per second. This is equal to seconds. So the units of RC are time. The units of L over R are time. And so this all hangs together. So this is very good. And emboldened by this success, I'm going to try and see whether I can just use dimensional analysis to kind of get a sense of what we're going to see when later in a future video we go on to consider a circuit with an L and a C in it. So what can I make from an L and a C? Well, I notice that suppose I just multiply them. And I ask myself, what are the units of LC? Well, the units of LC are the units of RC times the units of L over R, so this is equal to seconds squared. So that tells me, gives me a hint, a very correct hint in fact, that when we analyze an LC circuit, there should be a characteristic time of some sort involved in that circuit. And the characteristic time should be the square root of LC, because the units of the square root of LC are seconds. I can flesh this hint out further by remembering in a circuit, what kind of terms do I get from L's and C's? Well, what about R's first of all? So in a circuit, R always comes with I. R always gets multiplied by I when we walk our way around a circuit like this. C always comes with a Q. And L always comes with a di dt. But remember that I is dq dt. And that means di dt is d squared q dt squared. So once we put L and C together, we're going to have terms in our equation that have a q in them, and terms in our equation that have a d squared q dt squared. Just to say we're going to have a second order differential equation for q. That's an oscillator equation. Oscillator equation describes functions that goes like this. They oscillate, like we saw in 801 when we discussed simple harmonic oscillators. Things that oscillate have periods. So just from these considerations and dimensional analysis, my guess is that when we analyze an LC circuit, we're going to find oscillatory behavior with a period that is proportional to the square root of LC. And we'll see a few videos from now that that guess is in fact correct.